Picture this, a place in the universe where nothing can enter, but everything is expelled, a cosmic fountain, endlessly pouring out light, energy, and matter into the void. This is not a black hole, where everything vanishes into darkness, but its mysterious opposite, a white hole. Tonight, as you settle in, let your mind drift into the vastness of space, where the rules of physics twist and turn, and where the universe holds secrets that defy our understanding. Imagine a realm where time flows backward, where the very fabric of reality bends, and where the impossible becomes possible. This is the story of white holes, the cosmic enigmas that challenge everything we think we know about the universe. So, wherever you are, whatever time it is, let's embark on this journey together. Close your eyes, take a deep breath, and let the mysteries of the cosmos carry you away. By the end of this story, you'll not only have explored the fascinating world of white holes, but also found yourself drifting into a peaceful, star-filled sleep. Ready? Let's begin. Now, let's take a closer look at what white holes truly are. Imagine a black hole, but in reverse. While black holes are known for their immense gravitational pull, sucking in everything that comes too close, white holes are thought to do the exact opposite. Instead of pulling matter and energy in, white holes are theorized to expel them outward, like a cosmic fountain that never stops flowing. They are regions of space-time where nothing can enter, but everything is pushed out with incredible force. This makes them one of the most fascinating and mysterious concepts in modern physics. Unlike black holes, which we can observe indirectly through their effects on nearby stars and gas, white holes remain purely theoretical. They exist as solutions to Einstein's equations of general relativity, but no one has ever detected one. Yet, the idea of a white hole challenges our understanding of the universe, suggesting that there might be places where the rules of physics are flipped upside down. As we explore this concept further, keep in mind that white holes are not just the opposite of black holes in behavior. They represent a whole new way of thinking about the cosmos. Now, let's step back in time to uncover how the idea of white holes first emerged. The story begins with Albert Einstein's groundbreaking theory of general relativity, which he introduced in the early 20th century. This theory revolutionized our understanding of gravity, describing it not as a force, but as the curvature of space-time caused by mass and energy. It was within this framework that the concept of white holes began to take shape. One of the key figures in this discovery was Karl Schwarzschild, a German physicist who, in the year 1916, found exact solutions to Einstein's equations. These solutions described what we now know as black holes, regions of spacetime, where gravity is so intense that nothing, not even light, can escape. But hidden within Schwarzschild's work was another intriguing possibility. The equations also suggested the existence of a mirror image to black holes, a region where matter and energy could only flow outward, never inward. This was the first mathematical hint of what we now call white holes. At the time, these solutions were seen as more of a mathematical curiosity than a physical reality. After all, the idea of a cosmic object that only expelled matter seemed too strange to be real. But as physicists continued to explore the implications of general relativity, the concept of white holes began to gain traction. They realized that if black holes could exist, then their theoretical opposites might also have a place in the universe. The birth of the white hole theory was not just a moment of scientific discovery, it was a challenge to our understanding of the cosmos. It forced physicists to consider the possibility that the universe might contain phenomena that defy our everyday experiences. And while white holes remain purely theoretical, their origins in the work of Einstein and Schwarzschild remind us that even the strangest ideas can emerge from the most fundamental laws of physics. As we move forward, let's explore how white holes compare to their more famous counterparts, black holes, and how these two cosmic phenomena might be connected in ways that continue to puzzle and inspire scientists today. Now, let's turn our attention to the fascinating dance between white holes and black holes, two cosmic phenomena that stand as opposites yet are deeply intertwined in theory. At their core, black holes and white holes represent two sides of the same coin, each governed by the same fundamental laws of physics, but behaving in strikingly different ways. Black holes are known for their immense gravitational pull, so powerful that nothing, not even light, can escape once it crosses the event horizon. They are cosmic vacuum cleaners, drawing in matter and energy, compressing it into an infinitely dense point, known as a singularity. In contrast, white holes are theorized to do the exact opposite. Instead of pulling matter in, they expel it outward, acting as cosmic fountains that spew energy and matter into the universe. If a black hole is a one-way street into oblivion, a white hole is a one-way street out of existence. Despite their opposing behaviors, black holes and white holes share a deep theoretical connection. Both arise from solutions to Einstein's equations of general relativity, and some physicists speculate that they could be two ends of the same cosmic tunnel. Imagine a black hole in one region of spacetime, swallowing matter and energy, and a white hole in another, expelling that same matter and energy. This idea has led to the intriguing possibility that black holes and white holes might be linked by wormholes, hypothetical bridges that connect distant points in spacetime. Another key difference lies in their stability. Black holes are thought to be stable, long-lasting objects that can persist for billions of years. White holes, on the other hand, are considered highly unstable. If they were to exist, they would likely be short-lived, expelling their contents in a burst of energy before collapsing or transforming into something else. This instability makes white holes even more elusive and harder to detect than their black hole counterparts. Yet, despite their differences, both black holes and white holes challenge our understanding of the universe. They push the boundaries of what we know about gravity, space-time, and the nature of existence itself. While black holes have been observed indirectly through their effects on surrounding matter, white holes remain purely theoretical, a tantalizing possibility that continues to inspire scientists and dreamers alike. As we continue our journey, let's explore how these two cosmic extremes might be connected through the mysterious concept of wormholes, and how this connection could reshape our understanding of the universe. Now, let's venture into the realm of wormholes, a concept that ties together the mysteries of black holes and white holes in a way that feels almost like science fiction. Wormholes, often referred to as Einstein-Rosen bridges, are hypothetical tunnels through spacetime that could connect two distant points in the universe. Imagine folding a piece of paper so that 2 points touch. This is the essence of a wormhole, a shortcut through the fabric of reality. The idea of wormholes arises from the same equations of general relativity that predict black holes and white holes. In fact, some physicists speculate that a black hole and a white hole could be connected by a wormhole, forming a cosmic bridge. Picture this: a black hole in one region of spacetime, pulling in matter and energy, and a white hole in another, expelling that same matter and energy. The wormhole would act as the tunnel linking these two extremes, creating a pathway that defies our everyday understanding of distance and time. But here's where things get even more intriguing. If wormholes exist, they could theoretically allow for faster than light travel or even time travel. By entering a black hole and emerging from a white hole, one might traverse vast cosmic distances in an instant or even move backward or forward in time. Of course, this is purely speculative, and the practical challenges are immense. Wormholes are thought to be incredibly unstable, requiring exotic matter with negative energy to keep them open. Without this, they would collapse almost instantly, making them impossible to traverse. Despite these challenges, the concept of wormholes continues to captivate scientists and storytellers alike. They offer a tantalizing glimpse into the possibilities of space-time manipulation and the interconnectedness of the universe. While we have no direct evidence of wormholes, their theoretical existence provides a fascinating framework for understanding how black holes and white holes might be linked. As we ponder these cosmic connections, let's turn our attention to how white holes have been portrayed in popular culture, where they often take on a life of their own, inspiring awe and wonder in audiences around the world. Now, let's step into the world of imagination and storytelling, where white holes have captured the minds of creators and audiences alike. In popular culture, white holes often serve as gateways to the unknown, symbols of cosmic wonder, or even plot devices that defy the laws of physics. From science fiction novels to blockbuster movies, these mysterious phenomena have been reimagined in countless ways, shaping how we perceive the universe and its possibilities. Take, for example, the iconic science fiction series Doctor Who, where white holes are portrayed as sources of immense energy and potential. In one memorable episode, a white hole becomes a key element in saving the universe, showcasing its power to expel matter and energy in dramatic fashion. This portrayal not only entertains, but also sparks curiosity about the real science behind these cosmic phenomena. Similarly, in literature, white holes have been used as metaphors for rebirth or transformation. Authors often depict them as cosmic exits, where characters escape the confines of their reality or discover new dimensions. These stories tap into the human fascination with the unknown, using white holes as a canvas to explore themes of exploration, survival, and the limits of human understanding. Movies, too, have embraced the allure of white holes. In the realm of visual storytelling, they are often depicted as dazzling, otherworldly portals, glowing with radiant energy. These cinematic representations while not always scientifically accurate, help bring the concept of white holes to life, making them accessible and exciting for audiences who might not be familiar with the underlying physics. What's fascinating is how these portrayals influence public perception. For many, white holes are no longer just theoretical constructs, but vivid, almost tangible elements of the cosmos. They inspire awe, fuel curiosity, and encourage people to ask questions about the nature of the universe. While science fiction may take creative liberties, it plays a crucial role in sparking interest in real scientific exploration. As we reflect on these cultural depictions, it's clear that white holes have become more than just a scientific idea. They are a source of inspiration, a symbol of the boundless possibilities that lie beyond our understanding. And as we continue our journey, let's explore the scientific debate surrounding their existence, where theory meets reality in the quest to uncover the truth about these cosmic enigmas. Now, as we shift our gaze from the realm of imagination to the world of scientific inquiry, we find ourselves facing a compelling question. Could white holes actually exist? This is where the line between theory and reality becomes both fascinating and contentious. While white holes are a captivating idea, their existence remains one of the most debated topics in modern astrophysics. On one side of the debate, proponents argue that white holes are not just theoretical curiosities, but could be real cosmic phenomena. They point to solutions within Einstein's theory of general relativity, which mathematically allow for the existence of white holes. These solutions suggest that if black holes can exist, their opposites, white holes, might also be possible. Some scientists even propose that white holes could be the other end of black holes, connected through wormholes, creating a cosmic bridge across spacetime. This idea, while speculative, offers a tantalizing glimpse into how the universe might balance itself. However, skeptics raise important questions about the practicality of white holes. One major challenge is that white holes, by their very nature, would require conditions that seem to defy the second law of thermodynamics. Unlike black holes, which absorb matter and energy, white holes would expel them, effectively reversing the natural flow of entropy. This reversal is difficult to reconcile with our current understanding of physics, leading many to question whether white holes could ever form or sustain themselves in the real universe. Adding to the skepticism is the lack of observational evidence. While black holes have been detected through their gravitational effects and even imaged directly, white holes remain entirely theoretical. No telescope or instrument has yet captured a definitive sign of a white hole, leaving their existence firmly in the realm of speculation. Some scientists argue that even if white holes did form, they would be incredibly unstable, collapsing almost instantly under the weight of their own contradictions. Yet, the debate is far from settled. Some researchers suggest that white holes might not be standalone objects, but could instead be linked to the final stages of a black hole's life cycle. According to this idea, when a black hole evaporates through Hawking radiation, it might transform into a white hole, releasing its stored energy back into the universe. This hypothesis, while still unproven, offers a potential pathway for white holes to exist without violating the laws of physics. As we weigh these arguments, it's clear that the question of white holes pushes the boundaries of our understanding. Whether they exist or not, the very idea challenges us to rethink the rules of the cosmos and explore new possibilities. And as we continue our journey, let's turn our attention to the theoretical evidence that supports the existence of white holes, diving deeper into the mathematics and physics that make them such a compelling concept. Now, let's take a closer look at the theoretical foundation that makes white holes such a fascinating possibility. At the heart of this discussion lies Einstein's theory of general relativity, a cornerstone of modern physics that describes how gravity works on cosmic scales. Within this framework, white holes emerge as a natural, though puzzling, counterpart to black holes. Einstein's equations, which govern the behavior of spacetime, allow for solutions that describe both black holes and white holes. These solutions are mathematical predictions, showing that under certain conditions, regions of spacetime could exist where matter and energy are expelled rather than absorbed. One of the most famous solutions is the Schwarzschild solution, named after physicist Karl Schwarzschild, who first described the geometry around a non-rotating black hole. Interestingly, this same solution also describes a white hole when interpreted in reverse. What makes this so intriguing is that the mathematics doesn't distinguish between the two. A black hole and a white hole are essentially two sides of the same coin, depending on how you interpret the equations. This symmetry suggests that if black holes are real, and we know they are, then white holes might also be a valid possibility within the laws of physics. But the story doesn't end there. Another key piece of theoretical evidence comes from the concept of wormholes, hypothetical tunnels through spacetime that could connect distant regions of the universe, or even different universes altogether. Some solutions to Einstein's equations suggest that a wormhole could link a black hole to a white hole, creating a cosmic passageway. While wormholes remain speculative, their potential connection to white holes adds another layer of intrigue to the discussion. Quantum mechanics also plays a role in this theoretical puzzle. Some physicists propose that white holes could be the result of quantum processes, such as the evaporation of black holes through Hawking radiation. According to this idea, when a black hole completely evaporates, it might leave behind a white hole, releasing its stored energy back into the universe. This hypothesis, while still unproven, offers a potential bridge between general relativity and quantum mechanics, two fields that have yet to be fully unified. Of course, the theoretical evidence for white holes is not without its challenges. While the mathematics allows for their existence, the physical conditions required to form or sustain a white hole are far from straightforward. For instance, white holes would need to reverse the flow of entropy, a fundamental principle that dictates the direction of natural processes. This reversal is difficult to reconcile with our current understanding of the universe, leading many to question whether white holes could ever exist in reality. Despite these challenges, the theoretical evidence for white holes continues to inspire scientists and spark new ideas. They represent a fascinating possibility, one that pushes the boundaries of our understanding and invites us to explore the universe in new ways. As we continue our journey, let's turn our attention to another intriguing hypothesis, The idea that the Big Bang itself could have been a white hole, expelling matter and energy to create the universe as we know it. Now, let's explore one of the most captivating ideas in cosmology, the possibility that the Big Bang itself could have been a white hole. This hypothesis suggests that the birth of our universe might be intimately connected to the behavior of these mysterious cosmic phenomena. Imagine, for a moment, the universe as we know it beginning not with a singular explosion, but as the result of a white hole expelling matter and energy into existence. The concept builds on the idea that white holes are the opposite of black holes. While black holes pull everything in, never letting anything escape, white holes would theoretically do the reverse, pushing matter and energy outward. If we apply this logic to the Big Bang, it paints a fascinating picture. Instead of a single point of infinite density, suddenly expanding, the Big Bang could have been the moment a white hole began releasing the contents of a previous universe or another region of spacetime. This idea isn't just speculative, it has roots in the mathematics of general relativity. Some solutions to Einstein's equations suggest that a white hole could represent the other side of a black hole, connected through a wormhole. If this is true, then the Big Bang might not have been the absolute beginning of everything, but rather a transition point, a cosmic doorway through which the universe as we know it emerged. What makes this hypothesis so compelling is how it ties together two of the most profound mysteries in physics: the nature of the Big Bang and the behavior of black holes. If the Big Bang was indeed a white hole, it could help explain why the universe appears to have a finite age and why it continues to expand. It also raises the possibility that our universe is just one part of a larger cosmic structure, connected to other regions or even other universes through these theoretical passageways. Of course, this idea is not without its challenges. For one, the conditions required for a white hole to exist are incredibly extreme, and we have no direct evidence that such phenomena are possible. Additionally, the concept of a white hole Big Bang raises questions about what existed before the universe as we know it. If the Big Bang was the result of a white hole, what caused that white hole to form? These are questions that push the boundaries of our understanding and invite further exploration. Despite the uncertainties, the hypothesis offers a fresh perspective on the origins of the universe. It challenges us to think beyond the traditional narrative of the Big Bang and consider the possibility that our universe is part of a much larger, interconnected cosmic story. As we continue to unravel the mysteries of white holes, we may find that they hold the key to understanding not just the birth of our universe, but the very fabric of reality itself. With this intriguing possibility in mind, let's turn our attention to another cosmic mystery: the potential connection between white holes and dark matter, and how they might help explain some of the universe's most elusive phenomena. Now, let's shift our focus to another fascinating cosmic puzzle: the potential link between white holes and dark matter. Dark matter, as you may know, is one of the most mysterious components of the universe. It doesn't emit, absorb, or reflect light, making it invisible to our telescopes. Yet, its gravitational effects are undeniable, shaping galaxies and influencing the universe's structure on the largest scales. But what if white holes could help us understand this elusive substance? One intriguing idea is that white holes might be connected to the distribution or behavior of dark matter. Since white holes are theorized to expel matter and energy, some scientists speculate that they could release particles or forms of energy that interact weakly with ordinary matter, much like dark matter does. This raises the possibility that dark matter could be a byproduct of white hole activity, scattered across the cosmos in ways we're only beginning to imagine. Another angle to consider is how white holes might influence the gravitational fields around them. If white holes exist, their outward flow of energy could create unique gravitational signatures that mimic the effects of dark matter. For instance, the way galaxies rotate faster than expected could be explained not just by dark matter, but by the presence of white holes altering the gravitational landscape. This doesn't necessarily replace the need for dark matter, but it could provide a complementary explanation for some of the phenomena we observe. There's also the question of whether white holes could be a source of dark matter particles. If white holes expel exotic forms of matter or energy, these could include particles that don't interact with light, but still exert gravitational pull. This would align with what we know about dark matter and offer a potential mechanism for its creation and distribution throughout the universe. Of course, these ideas are highly speculative, and we're still far from having any concrete evidence. But the beauty of this hypothesis lies in its ability to connect two of the most profound mysteries in cosmology: the nature of white holes and the identity of dark matter. By exploring this connection, we might uncover clues that bring us closer to understanding both. As we ponder this possibility, it's worth noting how much of the universe remains hidden from our view. Dark matter, white holes, and the forces that shape our cosmos are all pieces of a puzzle we're still assembling. Each new idea, no matter how speculative, brings us one step closer to seeing the bigger picture. With this in mind, let's turn our attention to another intriguing aspect of white holes: their relationship with time reversal, and how they might challenge our understanding of the arrow of time itself. Now, let's venture into a concept that bends our understanding of time itself: the idea of time reversal and how it might relate to white holes. If black holes are known for pulling everything in, including time, white holes could represent the opposite, a cosmic phenomenon where time flows in reverse. Imagine a universe where the arrow of time points backward and events unfold in the opposite direction. This is the intriguing possibility that white holes bring to the table. In the realm of black holes, time slows down as you approach the event horizon, eventually appearing to stop entirely from an outside observer's perspective. But with white holes, the story flips. Instead of time slowing to a halt, it might accelerate outward, as if rewinding the cosmic clock. This reversal could mean that white holes don't just expel matter and energy, they might also expel time itself, creating a region where the usual rules of cause and effect no longer apply. One way to think about this is through the lens of Einstein's theory of general relativity. Just as black holes warp spacetime to the point where time and space switch roles inside the event horizon, white holes could do the opposite. They might create a region where time flows backward, offering a glimpse into a universe where the future influences the past. While this sounds like science fiction, it's a legitimate theoretical possibility that challenges our understanding of how time operates. This concept also ties into the idea of entropy, the measure of disorder in a system. In black holes, entropy increases as matter is consumed, aligning with the second law of thermodynamics. But white holes, if they exist, could reverse this process, decreasing entropy as they expel matter and energy. This would mean that white holes don't just defy gravity, they might also defy the natural tendency of the universe toward disorder, creating pockets of order in an otherwise chaotic cosmos. Of course, the idea of time reversal raises profound questions. Could white holes be portals to a universe where time runs backward, or are they simply mathematical curiosities with no physical reality? While we don't yet have answers, the very possibility invites us to rethink our assumptions about time, entropy, and the fundamental nature of the universe. As we explore these mind-bending ideas, it's worth reflecting on how much of the cosmos remains beyond our current understanding. White holes, with their potential to reverse time and challenge the laws of physics, remind us that the universe is far stranger and more wondrous than we often imagine. And with that, let's turn our attention to another fascinating aspect of white holes, their connection to quantum mechanics, and how this might help us unravel even more cosmic mysteries. Now, let's take a step into the quantum realm, where the rules of the universe become even more fascinating and mysterious. Quantum mechanics, the branch of physics that deals with the behavior of particles at the smallest scales, might hold the key to understanding white holes in ways that classical physics cannot. While general relativity gives us a framework for how white holes could exist, quantum mechanics could help us uncover how they might actually function in the real universe. One of the most intriguing ideas is the potential connection between white holes and quantum gravity. Quantum gravity is a theoretical framework that seeks to unify general relativity, which governs the large-scale structure of the universe, with quantum mechanics, which describes the behavior of particles at the smallest scales. This unification is one of the biggest challenges in modern physics, and white holes might offer a unique window into solving it. In the quantum world, particles can behave in ways that seem impossible in our everyday experience. For example, particles can exist in multiple states at once, a phenomenon known as superposition, or they can become entangled, meaning their properties are linked no matter how far apart they are. These strange behaviors could play a role in how white holes operate. Some scientists speculate that white holes might be the result of quantum processes happening at the edge of a black hole's event horizon, where the intense gravitational forces meet the bizarre rules of quantum mechanics. Another fascinating possibility is that white holes could be connected to the concept of quantum tunneling. In quantum mechanics, particles can sometimes tunnel through barriers that would be impossible to cross according to classical physics. This idea has led some researchers to suggest that white holes might be the result of matter and energy tunneling out of a black hole, effectively reversing the process of gravitational collapse. If true, this would mean that white holes are not just theoretical constructs, but could be real phenomena driven by quantum effects. Stephen Hawking's work on black hole radiation also ties into this discussion. Hawking proposed that black holes emit radiation due to quantum effects near their event horizons, causing them to slowly lose mass over time. Some theories suggest that this process could eventually lead to the formation of a white hole, where the energy and information that fell into the black hole are expelled back into the universe. This idea bridges the gap between quantum mechanics and general relativity, offering a potential explanation for how white holes might form and behave. While these ideas are still speculative, they highlight the exciting possibilities that arise when we combine the strange world of quantum mechanics with the cosmic scale of white holes. By exploring these connections, scientists hope to uncover new insights into the nature of gravity, spacetime, and the fundamental laws that govern our universe. As we continue to unravel these mysteries, it's clear that white holes are more than just the opposite of black holes. They could be a gateway to understanding some of the deepest questions in physics. And with that, let's turn our attention to another captivating aspect of white holes, their potential role in the multiverse, and how they might connect our universe to others beyond our own. Now, let's shift our focus to one of the most groundbreaking ideas in modern physics, Stephen Hawking's theory of black hole radiation, and how it might shed light on the mysterious behavior of white holes. Hawking's work revolutionized our understanding of black holes, suggesting that they aren't entirely black after all. Instead, they emit a faint form of radiation, now famously known as Hawking radiation. This discovery not only changed how we think about black holes, but also opened up new possibilities for understanding their theoretical counterparts, white holes. Hawking radiation arises from the strange interplay between quantum mechanics and gravity near a black hole's event horizon. According to quantum theory, empty space isn't truly empty. Instead, it's filled with pairs of particles and antiparticles that constantly pop into existence and then annihilate each other. Near a black hole's event horizon, however, one of these particles can fall into the black hole while the other escapes into space. The escaping particle carries away energy, causing the black hole to lose mass over time. This process is incredibly slow for large black holes, but it's a profound revelation. Black holes can, in theory, evaporate. So, how does this connect to white holes? Some scientists speculate that the energy and information lost through Hawking radiation might not simply disappear. Instead, they could be expelled through a white hole, effectively reversing the process. In this scenario, a white hole could be seen as the final stage of a black hole's life cycle, where all the matter and energy it once consumed are released back into the universe. This idea bridges the gap between black holes and white holes, suggesting that they might be two sides of the same cosmic coin. Hawking's theories also raise intriguing questions about the fate of information in the universe. According to quantum mechanics, information can never be truly destroyed. But if a black hole evaporates completely, what happens to all the information it swallowed? Some researchers propose that white holes could be the answer, acting as cosmic recycling centers that preserve and release information back into the universe. This idea not only ties into the behavior of white holes, but also helps address one of the biggest puzzles in physics, the black hole information paradox. While these ideas are still theoretical, they highlight the profound connections between black holes, white holes, and the fundamental laws of physics. Hawking radiation has already transformed our understanding of the universe, and its implications for white holes could take us even further. As we continue to explore these cosmic mysteries, we're reminded that the universe is full of surprises, waiting to be uncovered. With this in mind, let's turn our attention to another fascinating possibility: the role white holes might play in the multiverse, and how they could connect our universe to others beyond our own. Now, let's venture into one of the most mind-bending ideas in modern cosmology: the possibility that white holes could serve as gateways to other universes, offering a tantalizing glimpse into the multiverse. The multiverse theory suggests that our universe might not be the only one out there. Instead, it could be just one of countless universes, each with its own unique laws of physics and cosmic structures. But how do white holes fit into this picture? Some scientists propose that white holes could act as cosmic portals, connecting our universe to others in ways that challenge our understanding of reality. Imagine a white hole as a cosmic doorway, expelling matter and energy not just into our universe, but potentially into entirely different realms. This idea stems from the theoretical connection between white holes, black holes, and wormholes. While black holes pull matter in and white holes push it out, wormholes are often thought of as tunnels that could link distant points in space and time, or even different universes. If white holes are indeed the opposite of black holes, could they also serve as the exit points of these wormholes, funneling energy and matter into other dimensions? This concept ties into the broader multiverse theory, which suggests that our universe is just one bubble in a vast cosmic foam. Each bubble could represent a separate universe with its own unique properties. White holes in this scenario might be the bridges between these bubbles, allowing for the transfer of energy, matter, or even information across universes. While this idea is still speculative, it offers a fascinating way to think about the role white holes could play in the grand tapestry of existence. One of the most intriguing aspects of this theory is how it challenges our understanding of space and time. If white holes can connect universes, they might also allow for the possibility of time travel or alternate realities. For instance, what if the energy expelled by a white hole in our universe is the same energy that fuels the birth of another universe elsewhere? This would mean that white holes aren't just cosmic anomalies, they could be the engines of creation, driving the formation of new universes in ways we're only beginning to imagine. Of course, these ideas are still in the realm of theory, and much remains to be discovered. But the possibility that white holes could be gateways to other universes opens up a world of questions and opportunities. Could we one day detect evidence of these connections? And if so, what would that mean for our understanding of reality? As we continue to explore these cosmic mysteries, we're reminded that the universe, or perhaps the multiverse, is far stranger and more interconnected than we ever imagined. With this in mind, let's turn our attention to another fascinating question: How might white holes influence the expansion of our universe? And what could that tell us about the ultimate fate of everything we know? Now, let's shift our focus to one of the most pressing questions in the study of white holes. How do we observe something that, by its very nature, might be nearly impossible to detect? White holes, as we've discussed, are purely theoretical at this point, and their elusive nature makes them a challenge for astronomers and physicists alike. Unlike black holes, which can be observed indirectly through their gravitational effects on surrounding matter, white holes don't have a clear observational signature yet. But that doesn't mean scientists aren't searching for clues. One of the biggest hurdles in detecting white holes is their theoretical behavior. If a white hole is truly the opposite of a black hole, expelling matter and energy rather than absorbing it, it would need to exist in a state that defies our current understanding of physics. For instance, a white hole would require an enormous amount of energy to push matter outward, and this energy would have to come from somewhere. But where? And how? These questions make white holes not just difficult to observe, but also difficult to even imagine existing in our universe. Despite these challenges, researchers have proposed a few potential ways to detect white holes. One idea is to look for sudden bursts of energy in space that don't have a clear explanation. These bursts, known as gamma-ray bursts, are some of the most energetic events in the universe. While most gamma-ray bursts are thought to come from collapsing stars or merging neutron stars, some scientists speculate that a small fraction of these bursts could be the result of white holes expelling energy. If we could identify a gamma-ray burst with characteristics that don't match known astrophysical processes, it might be a candidate for a white hole signature. Another possibility is to search for anomalies in the cosmic microwave background, the faint glow of radiation left over from the Big Bang. Some theories suggest that white holes could leave imprints in this radiation, creating subtle distortions or patterns that might be detectable with advanced instruments. While this approach is still speculative, it offers a tantalizing way to search for evidence of white holes without needing to observe them directly. Of course, even if we do find potential signatures of white holes, confirming their existence would require a significant leap in our understanding of physics. For now, the search for white holes remains a blend of theoretical exploration and observational ingenuity. It's a reminder that some of the most fascinating mysteries in the universe are also the most elusive, pushing us to think beyond the limits of what we currently know. As we ponder the challenges of observing white holes, let's turn our attention to another intriguing question. Could gamma-ray bursts themselves hold the key to unlocking the secrets of these cosmic enigmas? Now, let's dive deeper into the fascinating connection between white holes and gamma-ray bursts. These bursts, some of the most powerful explosions in the universe, have long puzzled scientists. Typically, gamma-ray bursts are linked to events like the collapse of massive stars or the collision of neutron stars. But what if some of these bursts are not coming from these familiar sources? What if instead they are the cosmic fingerprints of white holes? Imagine a white hole, a theoretical object that spews out matter and energy instead of pulling it in. If such an object existed, It would release an enormous amount of energy in a short period, potentially creating a gamma ray burst. This idea has led some researchers to speculate that certain gamma ray bursts, especially those that don't fit the usual patterns, could be evidence of white holes in action. These bursts might be the universe's way of signaling the presence of these elusive objects. One of the key challenges in linking gamma ray bursts to white holes is distinguishing them from other cosmic events. Gamma ray bursts are incredibly energetic, and their origins are often shrouded in mystery. However, if scientists could identify a burst with unique characteristics, such as an unusual energy distribution or a lack of associated stellar remnant, it might point to a white hole as the source. This would require precise observations and advanced modeling to rule out other possibilities, but the potential discovery would be groundbreaking. Another intriguing aspect is the timing of these bursts. If white holes are indeed expelling energy, they might do so in sudden, explosive events rather than a steady stream. This aligns with the nature of gamma ray bursts, which are often short-lived but incredibly intense. The idea that a white hole could produce such a burst adds another layer of complexity to our understanding of these cosmic phenomena. It also raises questions about the conditions that might trigger such an expulsion of energy. Could it be the result of a black hole transforming into a white hole, or is it something entirely different? While the connection between white holes and gamma ray bursts remains speculative, it opens up exciting possibilities for future research. By studying these bursts in greater detail, scientists might uncover clues that bring us closer to understanding whether white holes exist and how they operate. It's a reminder that the universe is full of surprises, and sometimes the most mysterious events can lead to the most profound discoveries. As we explore this intriguing hypothesis, let's turn our attention to another cosmic puzzle: how white holes might influence the expansion of the universe itself. Now, let's shift our gaze to the grand stage of the cosmos and explore how white holes might play a role in the expansion of the universe. The universe is not static. It's constantly stretching, with galaxies moving farther apart over time. This phenomenon, known as cosmic expansion, has been a cornerstone of modern cosmology since its discovery. But what if white holes, those mysterious theoretical objects, have a part to play in this vast cosmic dance? One intriguing idea is that white holes could contribute to the universe's expansion by injecting energy and matter into space. Unlike black holes, which pull everything in, white holes expel matter and energy outward. If white holes exist, their explosive ejections could act as tiny cosmic engines, pushing the fabric of spacetime outward and accelerating the expansion of the universe. This would add a new layer to our understanding of what drives the universe's growth, suggesting that it's not just dark energy at work, but also these enigmatic objects. Another angle to consider is the relationship between white holes and the early universe. Some theories propose that the Big Bang itself could have been a white hole event, with an unimaginable amount of energy and matter being expelled to create the universe we see today. If this is true, then white holes might not just influence the expansion of the universe, they could be the very reason it exists. This idea ties white holes to the fundamental question of how the universe began and how it continues to evolve. But how would we detect such an influence? One possibility lies in the distribution of matter and energy across the cosmos. If white holes are actively contributing to cosmic expansion, their effects might be visible in the way galaxies and galaxy clusters are arranged. Scientists could look for patterns or anomalies in the large-scale structure of the universe that hint at the presence of these objects. Additionally, the energy expelled by white holes might leave subtle imprints in the cosmic microwave background, the faint afterglow of the Big Bang, offering clues to their existence. Of course, these ideas are still speculative, and much work remains to be done to explore them fully. But the possibility that white holes could influence cosmic expansion opens up exciting new avenues for research. It challenges us to rethink our understanding of the universe's growth and consider the role of these mysterious objects in shaping the cosmos. As we ponder the potential impact of white holes on the universe's expansion, let's turn our attention to another profound question. What role might white holes play in the ultimate fate of the universe? Now, let's venture into one of the most profound questions in cosmology. What role might white holes play in the ultimate fate of the universe? The universe's destiny has long been a subject of fascination and debate, with theories ranging from the Big Crunch to the heat death. But white holes, with their unique properties, offer a fresh perspective on how the cosmos might evolve over unimaginable timescales. One compelling idea is that white holes could be part of a grand cosmic recycling process. Imagine a universe where black holes, over trillions of years, slowly evaporate through Hawking radiation, releasing their trapped energy back into space. Some scientists speculate that this energy could eventually give rise to white holes, which then expel matter and energy anew. In this scenario, white holes would act as cosmic rebirth engines, transforming the remnants of dead stars and galaxies into the building blocks of new ones. This cyclical process could mean that the universe doesn't simply end in cold, empty darkness, but instead undergoes endless cycles of renewal. Another theory suggests that white holes might be connected to the concept of a multiverse. If our universe is just one of many, white holes could serve as bridges between them, funneling matter and energy from one cosmos to another. This would mean that the fate of our universe isn't isolated, but intertwined with the destinies of countless others. In this view, white holes could be the key to understanding not just how our universe ends, but how it connects to a larger, more complex cosmic tapestry. But what about the universe's expansion? If white holes are indeed contributing to cosmic growth, as we discussed earlier, their role in the universe's fate becomes even more intriguing. Some models propose that white holes could counteract the effects of dark energy, slowing down or even reversing the expansion of the universe. This could lead to a scenario where the universe eventually collapses back in on itself, setting the stage for a new Big Bang. Alternatively, white holes might work in tandem with dark energy, ensuring that the universe continues to expand forever, but in a way that's far more dynamic and interconnected than we currently understand. Of course, these ideas are still in the realm of speculation, and much remains to be discovered. Yet, the very possibility that white holes could influence the universe's fate invites us to rethink our understanding of time, space, and existence itself. It challenges us to consider that the cosmos might not have a single, linear destiny, but instead a complex, ever-evolving story shaped by forces we are only beginning to comprehend. As we reflect on the potential role of white holes in the universe's ultimate fate, let's turn our attention to another fascinating puzzle. How might white holes help resolve the black hole information paradox? Now, let's explore one of the most puzzling questions in modern physics. How might white holes help resolve the black hole information paradox? This paradox lies at the heart of a fundamental conflict between quantum mechanics and general relativity, and it challenges our understanding of how information behaves in the universe. At its core, the paradox asks, what happens to the information about matter that falls into a black hole? According to quantum mechanics, information cannot be destroyed, but black holes seem to defy this principle by trapping everything within their event horizons, leaving no trace of what fell in. This contradiction has baffled scientists for decades, but white holes might hold the key to unraveling this mystery. One intriguing possibility is that white holes could act as cosmic escape routes for information. If black holes are the ultimate cosmic vacuums, white holes could be their counterparts, expelling the very same information that black holes absorb. In this scenario, the information swallowed by a black hole wouldn't be lost forever, but instead re-emerge through a white hole, preserving the universe's informational balance. This idea aligns with the concept of quantum entanglement, where particles remain connected across vast distances, suggesting that information might somehow be transferred from black holes to white holes through hidden quantum channels. Another theory proposes that white holes could be the final stage of a black hole's life cycle. As black holes evaporate over time through Hawking radiation, they might eventually transform into white holes, releasing all the information they once consumed. This process would ensure that no information is ever truly lost, resolving the paradox in a way that satisfies both quantum mechanics and general relativity. It's a cosmic recycling system where black holes and white holes work together to maintain the universe's informational integrity. But how does this fit into our broader understanding of the cosmos? If white holes are indeed preserving information, they could provide a crucial link between the microscopic world of quantum particles and the macroscopic realm of black holes and galaxies. This connection might help bridge the gap between quantum mechanics and gravity, two of the most fundamental yet seemingly incompatible forces in nature. By offering a way to preserve information, white holes could bring us closer to a unified theory of physics, one that explains the behavior of the universe on both the smallest and largest scales. As we ponder these possibilities, it's clear that white holes are more than just theoretical curiosities. They could be the missing piece in our quest to understand the universe's deepest mysteries, from the fate of information to the nature of spacetime itself. And as we continue to explore their potential, we're reminded that the cosmos is full of surprises, waiting to be uncovered by those who dare to ask the big questions. With this in mind, let's turn our attention to another fascinating aspect of white holes, their connection to exotic matter and how it might shape their existence. Now, let's shift our focus to a concept that sounds like it belongs in science fiction, but is deeply rooted in theoretical physics. Exotic matter, this strange and mysterious substance, plays a crucial role in the formation and stability of white holes, setting them apart from the ordinary matter we encounter in our everyday lives. Unlike normal matter, which follows the familiar rules of physics, exotic matter defies these rules in ways that challenge our understanding of the universe. Exotic matter is theorized to possess properties that are quite literally out of this world. For instance, it might have negative energy or negative mass, meaning it could repel rather than attract other forms of matter. This peculiar behavior is essential for the existence of white holes. While black holes rely on the immense gravitational pull of normal matter to trap everything within their grasp, white holes would require something entirely different to expel matter and energy outward. Exotic matter could provide the necessary mechanism, acting as a kind of cosmic pressure that pushes rather than pulls. One of the most intriguing aspects of exotic matter is its potential to stabilize white holes. In theory, white holes are highly unstable, as their tendency to expel matter would cause them to dissipate rapidly. However, exotic matter could counteract this instability, creating a delicate balance that allows white holes to exist, even if only for a brief moment. This balance would be akin to a cosmic seesaw, where the repulsive force of exotic matter offsets the natural tendency of white holes to collapse or evaporate. But what exactly is exotic matter, and how does it differ from the matter we know? Normal matter, like the atoms that make up stars, planets, and even our own bodies, is governed by the laws of classical physics. It has positive mass, positive energy, and interacts through the familiar forces of gravity and electromagnetism. Exotic matter, on the other hand, operates outside these boundaries. It might exist in states that are only possible under extreme conditions, such as those found in the hearts of black holes or the early moments of the Big Bang. The connection between exotic matter and white holes also raises fascinating questions about the nature of spacetime itself. If exotic matter can stabilize white holes, it might also play a role in other cosmic phenomena, such as wormholes or even the expansion of the universe. Some scientists speculate that exotic matter could be the key to creating stable wormholes, hypothetical tunnels through spacetime that could connect distant parts of the universe. While this remains speculative, it highlights the profound implications of exotic matter for our understanding of the cosmos. As we explore these ideas, it's important to remember that exotic matter is still a theoretical concept. No one has yet observed it directly, and its existence is inferred from the mathematical solutions to Einstein's equations. Yet, the possibility of exotic matter opens up new avenues for understanding white holes and their place in the universe. It challenges us to think beyond the familiar and imagine a cosmos filled with phenomena that defy our everyday experiences. With this in mind, let's turn our attention to another intriguing aspect of white holes, their relationship to the arrow of time, and how they might challenge our understanding of entropy and the flow of time itself. Now, let's venture into a concept that bends the very fabric of our understanding: the arrow of time and its relationship to white holes. Time, as we experience it, flows in one direction forward. This unidirectional flow is often tied to the concept of entropy, the measure of disorder in a system. In our everyday lives, entropy tends to increase, meaning things naturally move from order to chaos. But what if white holes could flip this idea on its head? White holes, by their very nature, suggest a reversal of this process. While black holes are known for pulling matter and energy inward, increasing entropy in their surroundings, white holes are theorized to expel matter and energy outward. This expulsion could imply a decrease in entropy, effectively reversing the arrow of time within their vicinity. Imagine a cosmic clock running backward, where disorder gives way to order and chaos transforms into structure. It's a mind-bending idea that challenges everything we know about the flow of time. This reversal isn't just a whimsical thought experiment. It has profound implications for our understanding of the universe. If white holes can decrease entropy, they might represent regions where time operates differently, perhaps even flowing in the opposite direction. This would mean that within a white hole, the past and future could be inverted, creating a space where cause and effect are turned inside out. Such a phenomenon would force us to rethink the fundamental laws of physics, particularly those governing thermodynamics and the nature of time itself. The connection between white holes and the arrow of time also ties into the broader concept of time symmetry in physics. In many equations, time is treated as reversible, meaning the laws of physics work the same whether time moves forward or backward. However, our everyday experience tells us that time only flows in one direction. White holes could provide a real-world example of this theoretical time symmetry, offering a glimpse into how time might behave under extreme conditions. But how does this relate to entropy? Entropy is often seen as the driving force behind the arrow of time. As entropy increases, systems become more disordered, and time moves forward. If white holes decrease entropy, they could create pockets of the universe where time flows backward, or at least behaves in a way that defies our conventional understanding. This would mean that white holes aren't just cosmic anomalies. They could be windows into a universe where the rules of time and entropy are rewritten. As we ponder these ideas, it's worth considering the broader implications for cosmology. If white holes can reverse entropy, they might play a role in the ultimate fate of the universe. Some theories suggest that the universe could eventually reach a state of maximum entropy, known as heat death, where all energy is evenly distributed and no further work can be done. But if white holes exist, they could introduce a mechanism for reversing this process, potentially leading to a cyclical universe where entropy fluctuates and time itself becomes a dynamic, ever-changing force. This brings us to an even more intriguing possibility. Could white holes be connected to the origins of the universe? If the Big Bang was a white hole, expelling matter and energy into the cosmos, it might explain why the universe began in a state of low entropy. This would mean that the arrow of time, as we know it, is a direct result of the universe's birth from a white hole. It's a hypothesis that ties together some of the most profound questions in physics, from the nature of time to the origins of existence. As we continue to explore the mysteries of white holes, one thing becomes clear. They challenge us to rethink not just the cosmos, but the very nature of time itself. Whether they represent a reversal of entropy, a glimpse into time symmetry, or a key to understanding the universe's origins, white holes remind us that the universe is far stranger and more wondrous than we can imagine. And with that, let's turn our attention to another fascinating aspect of these cosmic enigmas, their potential connection to quantum mechanics, and how they might reshape our understanding of reality at its most fundamental level. Now, let's shift our focus to a concept that might sound like it's straight out of science fiction, but is deeply rooted in theoretical physics: the holographic principle and its potential connection to white holes. The holographic principle proposes a radical idea that the entire universe, with all its complexity and three-dimensional richness, might actually be a projection of information encoded on a two-dimensional surface. Think of it like a hologram, where a flat image creates the illusion of depth. In this case, the image is the universe itself, and the surface could be the boundary of a white hole. At first glance, this might seem unrelated to white holes, but when we dig deeper, the connection becomes fascinating. White holes, as we've discussed, are theorized to expel matter and energy rather than absorb it. This expulsion could be seen as a kind of cosmic output, where information about the universe is projected outward. If the holographic principle holds true, then white holes might serve as natural interfaces for this projection, acting as cosmic screens where the universe's information is displayed. This idea ties into one of the most puzzling questions in physics: where does information go when it enters a black hole? According to the holographic principle, information isn't lost. It's encoded on the black hole's event horizon, the boundary beyond which nothing can escape. But if black holes encode information, what about white holes? If they are indeed the opposite of black holes, they might represent the other side of the equation, where encoded information is released back into the universe. In this way, white holes could be the cosmic counterparts to black holes, completing the cycle of information in the universe. The holographic principle also raises questions about the nature of reality itself. If the universe is a projection of information, then what we perceive as three-dimensional space might be an illusion, a kind of cosmic hologram. White holes, with their ability to expel matter and energy, could be key players in this process, acting as conduits for the information that shapes our reality. This would mean that white holes aren't just theoretical curiosities, they could be fundamental to the very fabric of existence. But how does this all fit together? Imagine the universe as a vast, interconnected network of information. Black holes might act as data sinks, absorbing and encoding information, while white holes serve as data sources, releasing that information back into the cosmos. Together, they could form a dynamic system where information is constantly recycled, maintaining the balance of the universe. This idea aligns with the holographic principle's suggestion that the universe operates like a giant computer, processing and projecting information in ways we're only beginning to understand. The implications of this connection are profound. If white holes and the holographic principle are linked, they could provide a new framework for understanding the universe's structure and behavior. It might even offer clues about the nature of space, time, and reality itself. For instance, if the universe is a hologram, then the laws of physics, as we know them, might be emergent properties of this underlying information system. White holes, as part of this system, could hold the key to unlocking some of the deepest mysteries of existence. As we explore these ideas, it's worth considering how they might reshape our understanding of the cosmos. The holographic principle challenges us to think of the universe not as a collection of physical objects, but as a network of information. White holes, with their unique properties, could be the missing piece in this puzzle, helping us see the universe in a whole new light. And with that, let's turn our attention to another intriguing aspect of white holes: their potential role in the cosmic censorship hypothesis, and how they might help us understand the boundaries of spacetime. Now, let's take a closer look at how white holes might intersect with one of the most intriguing ideas in theoretical physics: Roger Penrose's cosmic censorship hypothesis. This hypothesis proposes that singularities, those infinitely dense points at the heart of black holes, are always hidden from view, shielded by an event horizon. In other words, the universe has a kind of cosmic modesty that prevents us from ever observing a naked singularity, where the laws of physics, as we know them, break down completely. But where do white holes fit into this picture? If black holes are the cosmic garbage disposals, swallowing matter and energy, white holes are their theoretical opposites, spewing out matter and energy instead. This raises an interesting question. Could white holes also harbor singularities? And if so, would these singularities be hidden, or could they exist without the protective cloak of an event horizon? The cosmic censorship hypothesis suggests that singularities must always be hidden, but white holes challenge this idea. Unlike black holes, which trap everything behind their event horizons, white holes are theorized to expel matter and energy outward. This means that if a singularity exists at the core of a white hole, it might not be hidden at all. Instead, it could be exposed, creating what physicists call a naked singularity. Such a scenario would violate Penrose's hypothesis, potentially forcing us to rethink our understanding of the universe's fundamental rules. This possibility has profound implications. If naked singularities exist, they could provide a window into the extreme conditions where gravity and quantum mechanics collide, offering clues about the nature of spacetime itself. However, their existence would also mean that the cosmic censorship hypothesis isn't as universal as we once thought. It would suggest that there are regions of the universe where the laws of physics, as we know them, no longer apply, opening up a Pandora's box of new questions and possibilities. Some physicists argue that white holes might still align with cosmic censorship, but in a different way. Instead of hiding singularities behind event horizons, white holes could act as cosmic filters, releasing energy and matter in a controlled manner that prevents the formation of naked singularities. In this view, white holes would still respect the spirit of Penrose's hypothesis, even if they don't follow its letter. This idea adds another layer of complexity to the relationship between white holes and singularities, highlighting the delicate balance between theory and observation. As we ponder these ideas, it's worth considering how they might reshape our understanding of the universe. The cosmic censorship hypothesis has long been a cornerstone of modern physics, but white holes challenge us to think beyond its boundaries. Whether they uphold or undermine this hypothesis, white holes remind us that the universe is full of surprises, and that even our most cherished theories are open to revision. With that in mind, let's turn our attention to another fascinating aspect of white holes, their potential role in the end of black holes, and how they might fit into the cosmic life cycle. Now, let's shift our gaze to a fascinating possibility. What if white holes are not just the opposites of black holes, but their ultimate destiny? Imagine a black hole, that cosmic vacuum cleaner, pulling in everything around it, never letting go. But what happens to all that matter and energy it swallows? Could it somehow find a way out, not through the black hole itself, but through its theoretical counterpart, the white hole? This idea suggests that white holes might represent the final chapter in the life cycle of a black hole, a cosmic rebirth where everything that was once consumed is expelled back into the universe. To understand this, let's revisit the life of a black hole. Over unimaginable stretches of time, black holes are thought to slowly lose mass through a process called Hawking radiation, named after the legendary physicist Stephen Hawking. This radiation causes black holes to evaporate, shrinking bit by bit until, theoretically, they might vanish entirely. But here's where things get interesting. Some scientists propose that this evaporation doesn't just lead to nothingness. Instead, it could trigger the formation of a white hole, a cosmic event where all the matter and energy the black hole once consumed is released back into the universe. Think of it like this: a black hole is a cosmic prison, trapping everything inside its event horizon, but a white hole could be the key to that prison, unlocking the door and setting everything free. This process would mark the end of the black hole's existence and the beginning of something entirely new. It's a cosmic recycling program where the universe takes what was lost and gives it a second chance. This idea isn't just poetic, it's grounded in some of the most cutting-edge theories in physics. For instance, quantum mechanics suggests that information about the matter and energy swallowed by a black hole can't simply disappear. It has to go somewhere. If white holes are the final stage of a black hole's life, they could provide a solution to this puzzle, ensuring that nothing is truly lost in the universe. Instead, everything is transformed, reshaped, and returned. Of course, this is still a highly speculative idea, and there's much we don't yet understand. But it opens up a thrilling possibility that the universe operates in cycles, with black holes and white holes playing complementary roles in the grand cosmic dance. Black holes gather and compress, while white holes release and renew. Together, they might form a cosmic balance, a never-ending cycle of creation and destruction. As we ponder this idea, it's worth considering what it means for our understanding of the universe. If white holes are indeed the final stage of black holes, they could offer a glimpse into the ultimate fate of matter and energy. They might even hint at a deeper truth, that nothing in the universe is ever truly gone. It's just waiting for its chance to begin again. With that thought in mind, let's turn our attention to another intriguing question. How might white holes influence the search for extraterrestrial life? Now, let's venture into a realm where science meets imagination, the potential role of white holes in the search for extraterrestrial life. If white holes truly exist, they could revolutionize our understanding of the cosmos and open up entirely new avenues for discovering life beyond Earth. Picture this: a white hole spewing out matter and energy from some distant corner of the universe. Could it serve as a cosmic beacon, signaling the presence of advanced civilizations? Or perhaps even act as a gateway for interstellar travel? One intriguing possibility is that white holes could be used as natural communication channels. Imagine an advanced alien civilization harnessing the energy expelled by a white hole to send signals across vast distances. Unlike traditional methods of communication, which weaken over long ranges, the sheer power of a white hole's output could make it an ideal transmitter. If we were to detect such signals, it might not just confirm the existence of white holes, but also provide our first evidence of intelligent life elsewhere in the universe. But the potential doesn't stop there. White holes might also offer a solution to one of the biggest challenges in space exploration: the vast distances between stars. If white holes are connected to black holes through wormholes, as some theories suggest, they could create shortcuts through spacetime. These cosmic tunnels could allow for faster than light travel, making interstellar journeys feasible. For an advanced civilization, a white hole might be the ultimate interstellar highway, enabling them to traverse the galaxy in ways we can barely imagine. Of course, these ideas are highly speculative, and the existence of white holes remains unproven, but they inspire us to think creatively about the possibilities. If white holes do exist, they could fundamentally alter our approach to the search for extraterrestrial life. Instead of scanning the skies for faint radio signals or distant exoplanets, we might one day look for the telltale signs of a white hole's activity: bursts of energy, unusual gravitational effects, or even the remnants of a wormhole. These could be the clues that lead us to our cosmic neighbors. As we ponder these possibilities, it's worth considering how they might reshape our understanding of life in the universe. If white holes are real, they could hint at a universe far more interconnected and dynamic than we ever imagined. They might not just be cosmic oddities, but key players in the grand story of existence, offering new ways to explore, communicate, and connect. With that in mind, let's turn our attention to another fascinating question: how do white holes challenge the very limits of our understanding of physics? Now, let's shift our gaze to the edges of what we know, where white holes stand as a challenge to the very foundations of physics. These mysterious cosmic phenomena don't justify our expectations. They force us to rethink the rules that govern the universe. At their core, white holes represent a profound puzzle, one that pushes the boundaries of our understanding and dares us to imagine new possibilities. One of the most striking ways white holes challenge physics is through their relationship with time. While black holes are often associated with the relentless pull of gravity and the irreversible flow of time, white holes suggest something entirely different. They hint at the possibility of time reversal, where the usual arrow of time might run backward. This idea isn't just a thought experiment. It's a direct challenge to our current understanding of how time operates in the universe. If white holes exist, they could force us to rewrite the laws of thermodynamics, which rely on the concept of time moving in one direction. But the challenges don't stop there. White holes also raise questions about the nature of singularities, those infinitely dense points at the heart of black holes. According to Einstein's theory of general relativity, singularities are regions where the laws of physics break down. But if white holes are the opposite of black holes, do they also contain singularities? And if so, how do they behave? These questions push us to explore the limits of general relativity and consider how it might need to be revised or expanded to account for such extreme phenomena. Perhaps the most exciting aspect of white holes is how they inspire new ideas in physics. For decades, scientists have struggled to reconcile general relativity with quantum mechanics, the two great pillars of modern physics. White holes might hold the key to bridging this gap. Some theories suggest that white holes could be connected to quantum gravity, a framework that seeks to unify these two seemingly incompatible theories. By studying white holes, we might uncover clues about how gravity operates at the smallest scales, shedding light on one of the biggest mysteries in science. Of course, these ideas are still in their infancy, and much remains to be discovered, but that's what makes white holes so fascinating. They represent the frontier of human knowledge, a place where our understanding is incomplete and the possibilities are endless. They remind us that the universe is far stranger and more complex than we can imagine, and that there's always more to learn. As we continue to explore the mysteries of white holes, we're not just pushing the limits of physics, we're expanding the horizons of human curiosity. And who knows, the answers we find might not just change our understanding of the cosmos, they might change how we see ourselves within it. With that in mind, let's turn to another intriguing question. How do white holes intersect with the concept of the multiverse, and what could that mean for our understanding of reality? Now, let's take a moment to step back and consider how white holes captivate not just the minds of scientists, but the imagination of all of us. These mysterious cosmic phenomena have a unique way of sparking wonder and curiosity, inviting us to dream about the possibilities that lie beyond the edges of our understanding. White holes, with their paradoxical nature and theoretical allure, remind us that the universe is a place of endless mystery, where the boundaries of reality are constantly being redefined. Think about it. White holes challenge everything we think we know about the cosmos. They flip the script on black holes, suggesting that instead of pulling everything in, they might be cosmic fountains, spewing out matter and energy into the universe. This idea alone is enough to ignite the imagination. What would it be like to witness such an event? Could we ever find a way to observe or even interact with a white hole? These questions don't just belong to physicists. They belong to anyone who has ever looked up at the night sky and wondered what lies beyond. White holes also tap into something deeper within us, a desire to explore the unknown. They represent the ultimate frontier, a place where the rules of physics, as we know them, might not apply. This sense of mystery is what drives scientists to push the boundaries of knowledge, but it's also what fuels the creativity of writers, artists, and dreamers. Science fiction, for example, has long been fascinated by the idea of white holes, often portraying them as gateways to other dimensions or as sources of unimaginable power. These stories, while speculative, reflect our innate curiosity about the universe and our place within it. But it's not just about the grand, sweeping ideas. White holes also remind us of the beauty of asking questions, even when we don't have all the answers. They encourage us to embrace uncertainty and to find joy in the process of discovery. In a world where so much feels predictable and routine, white holes offer a glimpse into a reality that is anything but ordinary. They remind us that the universe is full of surprises and that there's always more to learn. As we reflect on the role of white holes in the human imagination, it's clear that they do more than just challenge our understanding of physics. They inspire us to dream bigger, to think deeper, and to imagine a universe that is far more wondrous than we ever thought possible. And as we continue to explore these cosmic mysteries, we're not just uncovering the secrets of the universe, we're also discovering new ways to see ourselves within it. With that in mind, let's turn our attention to the future and consider how the study of white holes might shape the next chapter of space exploration. As we look ahead to the future of space exploration, the study of white holes opens up a realm of possibilities that could redefine our understanding of the cosmos. Imagine a future where humanity ventures beyond the confines of our solar system, not just to explore planets and stars, but to investigate the very fabric of spacetime itself. White holes, with their mysterious and theoretical nature, could become the next great frontier in this journey. They challenge us to rethink what we know about the universe and inspire us to develop new technologies and methods to explore the unknown. One of the most exciting prospects is the potential for white holes to serve as cosmic gateways. If they exist, these phenomena could offer pathways to distant regions of the universe, or even to other dimensions. This idea, while speculative, fuels the imagination of scientists and engineers who dream of one day harnessing such cosmic shortcuts. The concept of wormholes, often linked to white holes, has long been a staple of science fiction, but it also represents a tantalizing possibility for real-world space travel. By studying white holes, we might uncover clues about how to create or stabilize these theoretical passages, opening up entirely new avenues for exploration. Beyond the allure of interstellar travel, white holes could also revolutionize our understanding of fundamental physics. Their existence would challenge and expand our current theories, pushing us to develop new frameworks that better explain the behavior of matter, energy, and spacetime. This pursuit of knowledge could lead to breakthroughs in technology, from advanced propulsion systems to new forms of energy generation. The quest to understand white holes isn't just about satisfying curiosity. It's about unlocking the potential for transformative discoveries that could benefit all of humanity. Moreover, the search for white holes could drive innovation in observational astronomy. Detecting these elusive phenomena would require cutting-edge telescopes and instruments capable of observing the universe in unprecedented detail. This push for better technology could lead to advancements that enhance our ability to study other cosmic mysteries, from dark matter to the origins of the universe itself. In this way, the pursuit of white holes isn't just a niche endeavor, it's a catalyst for progress across the entire field of space science. As we continue to explore the cosmos, the study of white holes reminds us that the universe is full of surprises. They challenge us to think beyond the limits of our current knowledge and to embrace the unknown with a sense of wonder and determination. Whether or not we ever find definitive evidence of white holes, the journey to understand them will undoubtedly shape the future of space exploration, inspiring new generations of scientists, dreamers, and explorers to reach for the stars. And as we venture into this uncharted territory, we carry with us the hope that the universe has even more wonders waiting to be discovered. As we venture deeper into the mysteries of white holes, we find ourselves not just exploring the cosmos, but also reflecting on humanity's insatiable desire to understand the universe. The search for white holes is more than a scientific endeavor. It's a testament to our unyielding curiosity and our drive to uncover the truths that lie beyond the limits of our current knowledge. These theoretical phenomena remind us that the universe is far more complex and enigmatic than we can imagine, and they challenge us to keep asking questions, even when the answers seem out of reach. At the heart of this quest is a profound philosophical question. Why do we seek to understand the cosmos in the first place? For centuries, humans have looked to the stars not just for answers, but for meaning. White holes, with their paradoxical nature, embody this search for understanding. They represent the unknown, the unexplored, and the infinite possibilities that lie beyond our grasp. In pursuing them, we are not just chasing scientific breakthroughs, we are engaging in a timeless human tradition of seeking to make sense of the universe and our place within it. This pursuit also highlights the interconnectedness of science and philosophy. The study of white holes forces us to confront fundamental questions about the nature of reality, time, and existence. What does it mean for something to exist if we cannot observe it directly? How do we reconcile the theoretical with the tangible? These questions push us to think beyond the confines of traditional science and to embrace a more holistic view of the universe, one that acknowledges the limits of our understanding while celebrating the beauty of the unknown. Moreover, the quest for knowledge about white holes underscores the importance of imagination in scientific discovery. While they remain theoretical, white holes inspire us to dream, to hypothesize, and to explore ideas that might seem impossible today, but could become reality tomorrow. This blend of creativity and rigor is what drives progress, not just in astronomy, but in all fields of human endeavor. It reminds us that the pursuit of knowledge is as much about asking the right questions as it is about finding the answers. As we continue to explore the cosmos, the study of white holes serves as a powerful reminder of the boundless potential of human curiosity. It challenges us to remain humble in the face of the universe's mysteries, while also encouraging us to push the boundaries of what we know. Whether or not white holes are ever proven to exist, the journey to understand them enriches our collective knowledge and deepens our appreciation for the vast, awe-inspiring universe we call home. And in this endless quest for understanding, we find not just answers, but a deeper connection to the cosmos and to each other. As we bring our cosmic journey to a close, let's take a moment to reflect on the fascinating world of white holes and the profound questions they raise about the universe. These mysterious phenomena, often described as the opposite of black holes, challenge our understanding of space, time, and the very fabric of reality. While they remain theoretical, white holes inspire us to think beyond the limits of what we know and to imagine the infinite possibilities that lie hidden in the cosmos. Throughout this exploration, we've seen how white holes represent more than just a scientific curiosity. They embody humanity's enduring quest for knowledge and meaning. From their origins in Einstein's theory of general relativity to their speculative connections to wormholes, dark matter, and even the Big Bang, white holes remind us that the universe is full of wonders waiting to be discovered. They push us to question the nature of existence, the flow of time, and the boundaries of our understanding, inviting us to dream of what might lie beyond the horizon of our current knowledge. As we ponder these ideas, it's worth remembering that the pursuit of understanding is as much about the journey as it is about the destination. Whether or not white holes are ever proven to exist, the questions they raise and the theories they inspire enrich our collective imagination and deepen our connection to the cosmos. They remind us that the universe is a place of endless mystery and beauty, inviting us to explore, wonder, and dream. Now, as we prepare to drift into sleep, let's carry these thoughts with us. Picture the vast expanse of the universe, filled with stars, galaxies, and the enigmatic white holes that may one day reveal their secrets. Imagine the infinite possibilities that lie beyond our reach, waiting to be uncovered by future generations of explorers and dreamers. And as you close your eyes, let the gentle rhythm of the cosmos guide you into a peaceful, restful sleep, knowing that the universe is a place of endless wonder and that your curiosity is a part of its grand story. Thank you for joining us on this journey through the mysteries of white holes. If you enjoyed this exploration, don't forget to subscribe to our channel for more cosmic adventures. Hit the like button if you found this video inspiring, and ring the notification bell so you never miss out on our latest discoveries. Until next time, sweet dreams, and may your thoughts be as boundless as the universe itself.